And right, and then it gets really interesting when we come to arc length. So here we approximate the length of this by small segments which are straight, and then we do this finer and finer and see that we get a Riemann partitioning of the integral that looks like this. And this is also very natural, because what we're saying here is that length is the integration of speed. So here's a formula that you definitely should know. So chapter 11, length formula, integral from A to B, modulus R prime. So this as a vector, T. So that is the length formula. And then we have arc length. Parametrization, which is also important. Remember, so the arc length parameterization was okay. If this is my curve, I can go through it fast, I can go through it slow, or maybe fast in the beginning and then slow. It's still the same curve as long as I start here and end there. But there's once I have one parameterization, I can integrate, I can do this integral, but not for B, but any t along the curve. And then I get the length to that point where I am at time point t. And then I use, so that gives me a one-to-one function between time and length. And then I take the inverse of that and stick it into my original parameterization. So now my time axis, so to speak, is the length, meaning that anytime I differentiate, the speed or the vector will be a tangent vector of length 1. So the speed is always 1. I'm moving along the curve at constant speed 1. So this is a unique special parameterization that we call arc length parameterization. Of course, finding it was a bit difficult because it involves taking, so remember this, we had, here's A, here's B, and then we integrated the velocity, and we get a function from 0 to L, which is the length. And this is the one we want to use now as our time axis. We take the inverse here and stick it in to our parameterization, the original one. So now, since it involves taking an inverse, we didn't compute so many explicit arc length parameterization because it's usually hard to find inverses. But that doesn't mean that you shouldn't know how to do it in theory. So that is also explained here. So this, okay, if we have a graph, this is a particular incarnation of that formula, the integral on the blackboard behind me. And then there are examples here. So, okay. And then here's the arc length parameterization section, piecewise, smooth. Okay, you should know this. This is just terminology. So, yeah. So I just write here terminology for curves. .4 is omitted. So we don't do anything there. In fact, I think the rest of chapter 11 is omitted altogether. Let's look, where are we now? Yeah, it goes from 11.3 to 12.1. So this is where the course kind of really gets going, right? very hard to move in this document. But all right, so here we get going with graphs and partial differentiation. So level curves, graphs, okay, this is warm up. You should know what this is. Limits and continuity. So here comes then the definition of limit for several variables. And then we have a theorem basically saying that, same like in analysis one case, and any operation, multiplication, division, adding, subtracting, as long as you don't divide by zero, any operation composition of continuous functions will yield continuous functions. So with that, we see that all functions that were continuous as one variable object become continuous in the several variable context, and then we can start adding them together and as we want and achieve new continuous functions. So continuity is really not a big deal. Basically anything that is an expression you can write up of basic mathematical functions will be a continuous function, except that obvious discontinuities like arctangents has a discontinuity of pi half. So a function is continuous if this is true. There's also the epsilon delta definition. Well, that's the same thing. But okay, and here the book is a bit weak. We go more into this when we do the Weierstrass theorem. So an equivalent notion of continuity is every time you have a sequence of points, x and y, k, that converges to AB, the limit of f of x, y, k as k goes to infinity is equal to this. So that we had, it's in the lecture notes on the Weierstrass theorem, and this is something you should know also. So epsilon delta definition also. Okay, let me, what do I write here? So 12.1, and now I'm going to start chopping it up a bit more finely. So understand continuity sequence sequences and interesting examples. What do I mean by interesting examples? So it's important both here and for the derivatives later on to understand that you can't just check continuity by checking, in certain fixed directions. Same with the partial derivatives if they exist. So in the lecture notes, we have produced various counterintuitive examples of functions. For example, functions which are continuous along the coordinate axis at every point, but that fails to be continuous. You remember that one? It was I can write it up. So in polar coordinates, this is basically just sinus of 2 theta. But how the heck? So it's probably xy divided by x squared plus y squared. So what's interesting with this is that it is continuous along every line. It is actually a continuous function that emanates from zero, but the limit as you go to zero is different every time on every line. So it's not continuous at zero, despite looking continuous in every direction. So you have to, I mean, knowing examples like this, revisiting them when you go think about them, I mean, it shows a deeper understanding of these concepts. So, I mean, yeah. It's good, and we can, of course, in the exam ask something like that, you know, give an example of a function that yada yada. So it's good to have some idea of this type of examples. What was the question here? Of course, it is continuous to be hard. It's hard to be continuous at points you are not defined in. So, but this. So sinus of x divided by x, for example, it's not continuous at. It's not defined at zero, but we all agree that we can put it equal to 1 there, and then say that. And then we get that the corresponding function, which is sinus of x divided by x everywhere else, and then that particular value is a continuous function. So here we could have, you know, defined it to some value at zero if it had been the case that would have led to a continuous function, but there is no such value. So that's another way of putting it. Yeah. So okay, so let's move on here. The partial derivatives, here's just the definition. And then they introduced the tangent plane. And here is the thing. So the corresponding discussion I just had about continuity when it comes to differentiation, it is the same, right? So you can have functions that are partially differentiable at every point, but that are not differentiable. And differentiable means that the tangent plane is a good approximation of your function nearby a point, right? So for functions that have partial derivatives but are not differentiable, you can still make the tangent plane at every point. It's just that it's a crap approximation of the function nearby that point. So there's a clear distinction that most people miss between having partial derivatives and being differentiable. And the reason why most people miss this is because there's a theorem saying that if the partial derivatives exist and are continuous, then the function is differentiable, right? I'll show it in just a second. So for practical purposes, the distinction kind of disappears because most functions you ever see have this property that the partial derivatives are continuous, and then you have differentiability. But on a theoretical level, or where we are here, it's a clear distinction. Yeah. So this is highlighted more in the lecture notes than in the book. So they don't come to this differentiability until a bit later. So here they do higher order derivatives, which is nothing much to say. I mean, you just keep on differentiating and you get new functions. But there's the theorem, the equality of the mixed partials. And of course, this is one of the important theorems of the course. So this you should know. And now we have no oral exam, but otherwise I would definitely put this proof up as something to understand. So if you're interested in learning math, as opposed to just passing the exam, I would still recommend you go through the proof of key concepts, for example, that one. Chain rule comes next. Okay. So of course you should know the chain rule. So it has comes in a few different incarnations, and then the final version is this, where we think of derivatives as matrices, and the chain rule provides matrix multiplication. But here they start out with simpler cases. So you have one function of two variables and then a change of variables. So examples, homogeneous functions, just skip that completely. Okay, and then finally here comes differentiability. But we skipped, okay, we went over here, there's an important section. Higher order derivatives, okay. Okay, so here they start to do changes of variables in partial differential equations, right? So Laplace equation in polar coordinates and all of that. And this is good because we had the lecture notes are much more extensive here also. So we worked out several examples of how you can solve partial differential equations using a given change of variables. So this is something you should know as well. Let me start writing because now it gets a lot. So, okay, I don't do it section by section, but just like this. So,
the video is frozen.
Oh. Lund. Hello again, can you hear me? All
Yes.
right, so I don't know what went wrong, but okay, so let me start writing up this, what I said. So we have partial derivatives tangent plane and differentiability. So knowing the distinction there, just because the tangent plane exists doesn't mean you have a differentiable function. A differentiable function is much more. I'll show, that's in 12.7, so I'll show that soon. Then, okay, what else did we have? We have the theorem on mixed partials. In terms of the higher order derivatives, we have the Hessians that you have to understand because they come in later when we do Taylor. So the Hessians, you remember, it's this guy. Okay. Then we have the chain rule. So all versions I write. So the most general one being, you know, you have a function f goes from Rm into Rn, and then you have a function g goes from Rn into Rp, and then f, so g composed f differentiated is g differentiated at f times f differentiated, and there's a matrix multiplication. So this is a p times n matrix, and this is an n times m matrix. So together that becomes, you know, the n directions eat up, and you get a matrix which is n times p, which it should be. So this is a very beautiful generalization. Okay. And then we have this. So there are two things here which goes to the lecture notes that are not so well explained in the book. One is Weierstrass theorem, and the other thing is how to use changes of variables to solve PDEs. So that there are some examples in the book, but it's recommended to really go to the lecture notes for that class as well. So plus lecture notes on Weierstrass theorem and how to solve PDEs with change of variables. How to solve PDEs with change of variables, it says. Okay. Right, so here we were, this is Laplace equation in polar coordinates. And then we come to this idea of first order, the linearization or the Taylor expansion of first order. So we don't, okay, before we had the tangent plane, but now we start to think of the tangent plane as some sort of approximation of the curve, which leads to this definition of differentiability, yeah? Which is a limit process involving h and k, where these are the perturbation parameters. So it doesn't have a fixed direction in space. It's just like in a ball around point. You need to have some homogeneous, you know, control there. So that's saying much more than partial derivatives, which just talks about what happens in certain specific directions. So if this is true, then the function is differentiable. Is much more than being partially differentiable. And then there's a theorem here, theorem 4, that I mentioned already. So if these guys are continuous, the partial derivatives, then f is differentiable there. And of course, this is something you should know. Okay, and then this thing with differentials, I don't like it. It's more like a notation issue. So it's not something I will test you on directly. Okay. So here comes this with, now if you have functions from n space to m space, so this is the most general version of the chain rule, then the derivative is this Jacobian matrix, not the same as the Jacobian. And the chain rule for Jacobi, the chain rule in terms of these Jacobi matrices looks like this. Okay, so written shorter, here's the formula, which is the one I wrote on the blackboard. So this you should know. So here the ends about Legendre transform and whatever, you just skip that completely. And now I want to have a break, but let's finish chapter 12 first. So gradient and directional derivatives, yes, you should know what this is. And you should understand their geometric meaning, right? So the gradient, if you have a function of n variables, the gradient is still in Rn, which sometimes confuses us. Let's say the variables are 2. Then we often visualize the function as something in R3, right? Because we add an axis for the value. And then people get confused and think that the gradient should also be in R3. No, it's in R2. It's down in the plane. And it points in a direction, and it points in the direction where the curve has the steepest increase, right? You take a scalar product of that with any other direction, and you get the increase in that direction if the scalar product you take is with a unit vector. So that comes here. Here's this discussion of geometric properties of the gradient vector. Okay. And yeah, now comes implicit functions as well. Let me stop here because these implicit functions, oh, and then there's Taylor also. It requires a new blackboard for that. So here I just add understand gradients mathematically and geometrically. So gradient and directional.
It's frozen again.
So this is now 12.127. Okay, and then on the next blackboard I'll start with 12.8. But before that we shall have a break. So break starts now. All right. So it seems the technology is not on our side today. Anyways. So the implicit function theorem, apart from what's written in the book about it, we have lecture notes, we have additional notes on the implicit function theorem written by Alexander Alderman, and of course, for those of you who read Callahan's book, there are two entire chapters devoted to implicit function theorem and also inverse function theorem, which is somehow the sibling there. In terms of the exam, I mean, these are very deep theorems, and to the degree that you understood them, it's up to you. I mean, but this is difficult to check. So in terms of the exam, we will just basically check that you know how to solve, how to use them in practice. And that boils down to rather simple things, right? So either you have one function f of two variables and you want to solve for one of variables as a function of the other, or you have a function of 3 variables. And then if it's one function, you can solve either for x, y, or z as a function of the other two, like we did yesterday on the blackboard. And then, yeah, you just need to check if you want to solve for a c, for example, that the third derivative or the c derivative of f is non-zero at that point that you want to solve. Then there's this really interesting observation that you can compute. If you have a concrete point, you can compute. Once you know that c exists as a function, you can use the chain rule to differentiate this with respect to x, taking into account that c is now a function of x, and then you get formulas like this one. And that you can use to compute the value of the partial derivatives of the unknown function c at the point. So you can do, if you repeat this process, you do a Taylor expansion of c. Just repeat long enough. So that's a process you're supposed to know how to perform in practice, right? So systems of equations, now they actually have 4 variables. Ooh. And that's as difficult as it's gonna get, right? So if you know these here, if you study them, then you should be fine in terms of the exam, I would say. Right. So you should know the statement of the full implicit function theorem, which comes to solve for the y variables. There are n of them if you have n equations, and then you have to check that the corresponding sub-matrix of the Jacobian matrix with only those derivatives, that one has a non-zero, well, that it's invertible basically, so the determinant is non-zero. If you have that, then you can solve this. And also remember, I did in my class here, so just in general, like to memorize this thing, if you think of F1 up to Fn as just linear equation systems, and you just imagine doing Gaussian elimination here, then this becomes very, very natural, this condition here, that if you do Gaussian elimination on this system, if the matrix coefficients for the y's is an invertible matrix, then your elimination system is going to work out. So you get y1 equals to yada yada, y2 equals to yada yada. So you put them free on a diagonal and get them as depending on x only. So this is sort of a lifting of Gaussian elimination in a sense there. So I would write here, mainly look at examples as a means to prepare for the exam. So okay. 12.8 implicit and inverse function theorem. I say review examples on how to use these. The inverse function theorem is actually a special case of the implicit function theorem. It's simpler. It just says that a function of n variables into n variables is invertible locally if its Jacobi matrix is invertible, right? So you know how to use these. So primary use is like, okay, is this function invertible? Or can I solve for C as a function of X and Y at this point? A bit more advanced question would be, can I solve for C and then, you know, give me the Taylor expansion? Right, so that's what I mentioned before. I wrote there, know how to compute the Taylor coefficients of the implicit function. That is, yeah. Moving on to Taylor series. So with the Taylor coefficients, I just mean the derivatives to some degree. Taylor series, so theoretically not difficult. What we do is we do a Taylor series in one variable in the direction of a line, right? So we fix the direction h and k in space at the point a, b. We do, you know, we take t times that, and then we just move in a line and do a Taylor of that at the point 0 in one variable, and that gives us the several variable Taylor theorem. The difficulty with Taylor's theorem is to find a decent way to write it down, because these sort of directional derivatives that we get becomes increasingly hard to compute. And then there's this nice way of, instead of, so here if you just do direct computation, you get stuff like this, okay? And then there's this beautiful way of thinking of differentiation as a operator on functions. So it takes a function in and spits out a new function. And then we can all of a sudden start doing algebra with the differential operators. So then instead of writing a long, ugly thing like this, or even worse, this one, we can write hd1 plus kd2 to the power of 3, which looks very nice. And then armed with that, the Taylor expansion here is just, it looks precisely like the ordinary one. So 1 over m factorial. And then instead of just differentiation to the order m, which you would have in the wonder variable, you have hd1 plus kd2 and that to the power of m. So this is a nice way of memorizing it. Then if you want to expand this, you get a very ugly expression, which with summation notation looks like this. But here to expand this guy, you need to know this binomial theorem, which we also revisited, right? So in terms of exercises, you should be able to compute these ones. We'll never do it beyond the order 2. And then for the second order version, we can express this quadratic part here with the Hessian as well. And that leads to this classification of into local minima and whatever. So the Hessian can have the positive semi-definite or negative semi, but we come to that. Here's this approximating implicit functions. So now that's what I wrote up before. So here they have an example on that. So this equation implicitly defines y as a function of x, and then they use the equation itself to get derivatives of the unknown function f. To arbitrary order, as you see down here. Okay, so what should we write here? 12.9. Different formulas for Taylor. In particular, this one in my mind, the most beautiful one. This one is also easily generalized to higher orders, to more variables. And then, okay, so this is not going to infinity, this goes to n, and then at each stage, or n minus 1 maybe, and then you have this Rn hk, which is a remainder. We don't know the exact form of this remainder, we only know that it is ordo hk to the power of n, right? If you want, you can always use the one-dimensional Taylor and the Lagrange remainder to get an estimate here on this guy. But we usually don't go that far. At least we don't have that on the exams. What we do have on the exams is alternative ways of getting this, because these derivatives are sometimes difficult to compute. So as we did yesterday on the exam, there's this uniqueness theorem that if you have a polynomial here of order n minus 1 and a remainder term which is order n, then you know that this polynomial is your Taylor polynomial. So that's like a shortcut to get it. So I write here uniqueness of Taylor polynomials. This is in the lecture notes. I don't think they have it here in the book. Let me write here also the binomial theorem, because it connects very naturally to this. That's also in the lecture notes. So you should know the binomial theorem. I always confuse if it's binomial or binomial. It's a polynomial, so it should be binomial, I guess. Questions? So let's see where we are. So in terms of the course plan, all right, chain rule, gradient, inverse and implicit function theorem. Right. Okay, so then what remains is the assorted topics in chapter 13 and then the integration theory part. So extreme values here. Yeah, you should just know how to solve problems with extreme values. So this terminology, of course, important. Critical point means the derivative is 0, the gradient. Singular point, it doesn't exist. And boundary point, well, it's on the boundary. So this is not really rocket science. And then there's this observation more than a theorem that if you have a maximum, local max or local minimum, it has to be either one of these three alternatives. So that gives you like a blueprint for how to look for maximums and minimums simply by going through computing all points in these three cases. Yeah, and then, right, so then, but here we have this thing then that if we want to classify the point, is it a saddle point like this one, or a local minimum? So then we come to this classification, and that means we have to look at the second order Taylor. So second derivative test, usually we just do this in two variables, but typically Hessian matrix. is an n by n matrix. And then if all these eigenvalues are positive, you get a global minimum here. And then there's a theorem which says that, well, the original function which you are approximating behaves the same way. So there is this, the Hessian can be positive definite, positive semi-definite, indefinite, negative semi-definite, and those semi-definite cases we don't know. So if all eigenvalues, so to speak, are, well, right, so here we have these three cases, right? So if this is, so if you just have a 2x2 matrix, you can do this ABC test instead, as long as you understand what this means. So this here is the same as the eigenvalues multiplied. So if both eigenvalues are, if one is positive and one is negative, you get that this thing here becomes negative. Oh, they wrote the B first. Okay, then it's the other way around. Well, anyways, so you have three cases here where you can say either f is a local maximum, minimum, or saddle point. And then there's a fourth case, which is when this thing equals to 0. That's the same as saying that one of the eigenvalues of the matrix is equal to 0. And then we don't know. So this is the semi-definite case. And then it can happen that you have a local max, a local min, or not. So it's important to also understand that we don't know. So here the lecture notes, again, give more information, especially with the terminology, and also alternative ways to solve this, right? So if you remember the exercises from that class, we instead of doing this kind of test, we just we looked at the second order term and did algebraic manipulations with it to see if we could write it as a sum of two squares. And if you have a sum of two squares, then you look at the sign there. If both are positive, then you know it's a local minimum and so on. So, okay, there are lots of things go in here in terms of computational tricks. There's not a lot of theory. So just write here, know how to find and classify extreme points with all that comes along with it. So Hessian, ABC test, this theorem here, where did it go? Second derivative test theorem, so theorem 3. So here I also write, see also lecture notes, because they are really giving more value than the book. So for additional tricks, but anyway, this deep understanding involved. Okay, so that's 13.1. 13.2, then we dropped this that we were on a compact set. So before we were on a set that had a nicely defined boundary, but of course many extreme value problems in real life or from physics, they have no boundary restrictions. So how do we deal with that? Well, that's also just, you have to learn by doing examples how that works. And basically, how it works is you have to somehow analyze the function at infinity, in the sense that you have to get some idea of what is the main term here, which is big when I go to infinity, and how does that one behave. So usually there are two categories. Either you find a direction where your function goes to plus or minus infinity, and then you just say that global extreme values do not exist. Or of course, you could have many special behavior at infinity, so it's not like either or here, but in terms of the exercises, it's an or, because if that doesn't happen, that it goes to infinity, what's going to happen in your exercises is that it goes to zero. And what you have then is, okay, the function is whatever, and then it goes to zero. So it means that outside the circle of very big radius, your function is less than, let's say, a half, or whatever number you want. And that means that if you found some extreme values inside your big circle with higher numbers than a half, or what you decide, then those are also global, right? Because outside everything is less than a half, and inside these are your extreme values. So that's how you deal with that. And this you should know how to solve for the exam. Here, Lagrange multipliers is not part of this course. It's part of the next course, so that's a good reason for taking the next course, because this is very, very useful. Or actually, you should probably take an independent course on optimization. Then we had this assorted topic, differentiating in integrals with parameters. Again, another computational tool that you should know how to master. There's not too much mathematical theory here. Well, of course, yeah, it goes in the understanding of what's going on. Well, yeah, there is this nice proof also about when you're allowed to do this, when you're allowed to take the derivative from outside and move it on the inside. And the proof here, or the theorem, says that you should check that the second derivative in some strip is bounded by a function. Oh, I thought it was going to freeze again. Do you still hear me? Hello?
We hear
Does
you, but
somebody
you're
still
not.
hear
Your
or not?
camera's not moving.
Hello? Can somebody hear me now? So, for how long was I gone? When did you leave? I hate this. I don't know what's wrong with the technology today. There we go. All right. So I was discussing differentiation inside the integral. Did you hear that? Ah, okay. Good. I kept my cursative vocabulary at a minimum. Then I'm getting a bit tired with this constant problems. Well, anyways, so yeah. So in the book, there's a theorem which says when you're allowed to differentiate under the integral. And let's remember ourselves. Okay, so here we could integrate between a and b. And in the book, I think they did it that they integrated in t and differentiated in x. Doesn't matter. But if you have some x0, and then there was this thing that, okay, so then the function value we get from integrating on this line. And in order to differentiate there, what you need is information in a small neighborhood. So basically, you could take a C and a D just slightly above and below. And what you need then is information about your second derivative in a box like this, right? So that makes the theorem a bit hard to apply. In terms of theory, I mean, so the book has one theorem with the second derivative. The lecture notes have another theorem with the first derivative. And really, it doesn't matter which one you learn. At the end of the day, if you take integration theory, you will learn like the best version of this theorem. So it comes back to but for what you're up to now, this is good enough. And there's also this theorem that as long as you're dealing with a compact set, so from a to b, not a generalized integral from minus infinity to infinity, in that case, these theorems also apply with that function g and so on. But as long as you have an a and a b and the function is smooth, so at least have two continuous derivatives, then you can always do differentiation inside the integral. And that was that, I added a page to the lecture notes because I don't think it's in the original lecture notes. So getting back here to screen sharing. Right, so you should know this theorem and how to use it. And then comes this thing, envelopes you can skip completely. But here it gets nice, so no. So the a and b in the integral can also depend on x, right? And then it gets even, so okay, so here's the chain rule, right? So this is when a and b of x depend on x, then you get this form here. And in the lecture notes, we explain this a bit more in depth, how you get this expression here. So you write, basically you introduce a function, like they do here, f of x, b, and a. You do chain rule on that, and you get this expression here. So so this is a formula you certainly want to remember for the exam. And okay, so I mean, I always think that it's good to go through all of the lecture notes, of course, in preparation for the exam, but sometimes I write C lecture notes when I think that lecture notes really have a bit of more or a different material than the book. Sometimes the lecture notes follow quite closely the book, and then, of course, it's not as important to go through the lecture notes. Okay, so that about that, and that concludes chapter 13. So we only have to deal with integration, and then we're done. Okay, so the theory for integrals, you should understand it, the basics, like how do we build integrals? How are the Riemann sums formed? What are these lower and upper sums? You should know it, you should be able to explain it. It doesn't mean that you should know the details of it, because to prove that a continuous function is integrable, for example, using uniform continuity and blah, 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 that's overcourse, and that's nothing that we can test you on the exam. So for the exam, don't worry about that. But understanding the basic construction, the ideas behind it, which is described here with the Riemann sum and also in the lecture notes, this is very important. Okay. So first you integrate over a square or a rectangle, and then you extend that to a more general domain. How did we do that? By simply extending the function so that the function was 0 outside of the domain of interest. And this creates then a sharp edge, right, of the function where it drops down to 0. So if the function is nice, like continuous, but the domain is fishy, like with a lot of, some sort of fractal curve, then you could still get something which is not integrable. So the question then comes, which functions and which domains allow for integration? And the answer is, well, at least if the function is continuous and the domain is Jordan. So Jordan meant that you could cover the boundary with rectangles of arbitrarily small total size, right? And then you ask yourself, okay, but which functions are Jordan? And then the answer was, as long as your boundary has a C1 parameterization, then it is Jordan. And all of this is in the lecture notes. And some of it is here in the book. But of course, the main important thing is to know how to compute integrals, and especially here also the triangle inequality. The rest of the computational rules here are very straightforward, but the triangle inequality is important to know. Okay, and then we come to iterated integration. So then we have this idea of simple domain, X simple and Y simple. Yeah, so here it's X simple. This one is Y simple. Why? Because on every line that cuts the domain, I'm going to go in at one point and go out at one point. And this means that I can describe my domain by a function C of X and D of X, telling me the upper and lower bound there. So if it is Y simple, the description is in terms of a function that depends on X, not the other. So it's, the order here is kind of flipped, right? Same X simple, then you have a function A of Y and B of Y that can describe the boundary of your domain. Okay, and then we do partial integration or iterated integration on that. So it looks like this. And this is, of course, a formula you should know. So, and the rest is just learning how to. So 14, understand basic idea of constructing the integral know how to compute it. Of course, using iterated integration. X/Y simple domains. Jordan domains. Or not etc. So, right. So again, the focus is on into computational skills rather than in terms of the exam, rather than a deep understanding of the theory. But you should, I mean, the question could be explain what's a Jordan domain, you know. So a bit of theory should also be considered when you review the material. Improper integrals, okay. The mean value theorem, I don't think I will give you a question on that, but generalized or improper integrals is of course important also to know how to compute. Okay, then come change of variables, and this is very important, especially the only real change of variables we will ever do is polar coordinates, spherical coordinates, or linear change of variables. So those three are the ones to focus on. So here is the theory for this. Right, and at the end of the day, we derive this determinant here that you stick in for change of variables, and I motivated this very carefully. If you remember that, then very good. But again, we don't have an oral exam, so hard to test. So let me write here. Change of variable, in particular, polar, spherical, and linear. Anything beyond that is most likely not going to show up. Well, I don't promise that, but anyway, these are the three most important ones, right? And then at the end of the day, we have triple integrals. That was just very much similar to the 2D situation. Well, with a bit of differences that now we have three directions. When you do iterated integrals, you can think of it as one-dimensional integral outside and a two-dimensional integral inside. And that gives us like the slice theorem. Or we flipped it around. We did first a one-dimensional integration and the remaining two-dimensional integral on the outside, which this one doesn't have a name, but those are two ways to go on about it. Okay, and then we have change of variable again. Here are the spherical coordinates. And that's it. No, there was also surface area. Okay. So again, if you remember the derivation of the formula for surface area, great. If not, make sure you remember this formula here, right? Then we had the slice formula for 3D integration, right? So how was that? So if I want to, I have some domain here D. in 3 variables. And this domain D has some sort of shadow down on the XY plane. So then the slice formula, it was cut out slices like this, in, for example, the YC direction, integrate over those slices in the YC, and then you integrate over X, yeah? So that's like, you think of this as a loaf of bread, and you chop it up, and then you measure the area of each bread and the thickness of each bread, and you sum up. The other option was that, okay, in each line here, I just integrate, yeah? So then down here on the shadow, for each point, I can integrate through a vertical line. And that gives me a value that then I can integrate down here on the shadow. And that was the other way of doing the iterated integration in 3D. So you always have 2 alternatives there, and one can lead to longer computation or impossible computation, whereas the other one can lead to shorter computations. So always good to have both in mind, especially at the outset of an example, and think which one will serve me best. And okay, right on time. It's 10 o'clock. I think I covered everything. Let me go and have a final look at the course plan. Yeah, that's it. So that's what you're supposed to know. I will take a photo of these 3 blackboards I wrote up and upload on the internet if you want to use it. Other than that, good luck. I'll see you on Friday, and I'll also be available next Thursday a bit for answering questions. And tomorrow I'm also available during lunch for questions. Should we? Yeah, okay, tomorrow. That's it. If there are no questions now. Yes, I did mention generalized integrals, so you should know that it's very important. Generalized integrals too. But I agree with you, they're not very different. So this, what I do here today is like an advice. I go through the whole book and I talk about what I think are key concepts of and what's important. It's not meant as only study this and then you're going to be fine. It's like, no, this is a course. If you know everything I told you today, for sure you will get a G. There is no, I mean, we designed the exam in a way that, you know, we hope that if you just study the main parts, you should get it. But you know, the life, there's always people that make mistakes, although maybe they understood it, but then you're nervous, or I don't know, you had a bad day. So it's always good to have a bit of a margin, usually around 50% pass the first exam. So that's a lot of stress for you to redo the exam, and it's a lot of work for us to correct your exams over and over. So, but if you want a good grade, I mean, there's no, like, just because maybe I didn't mention every detail that came into the course. I mean, so when you revisit the course, it's up to you how well you want to learn the material. And the more you learn it, the better chance you have, of course, of getting a 30 points on the exam. So just because I haven't mentioned something isn't a guarantee that it won't come on the exam. But these are the key points. If you know all of this, then for sure you will pass the exam. All right. So Jesper Larsson recommends you to drink a bottle of whiskey before the exam to cool your nerves. Well, as your teacher, I can't endorse that behavior, at least not before the exam, maybe after the exam. But all right, any other math-related questions? All right. Well, see you on Friday and enjoy the rest of today. Bye-bye.